Welcome to the Calculus, a collection of micro lectures, video lessons, and sample exercises. Let's learn the chain rule, or the rule in differentiating a composite function. Having learned the proven differentiation rules, which includes for algebraic or polynomial functions, rational functions, and trigonometric functions, let us dig deeper on one of the most common and most important rules in differentiation. We have here the chain rule. The chain rule is also known as the rule in differentiating a composite function. So here we are going to illustrate the point of having this rule and the rule itself. Let us say, for example, we have f of x being x to the power of 7 and g of x is, let's say, x cubed minus 4x squared plus 5x minus 10. If we are going to have our composite function, to which we learned before, in this manner, f of g of x, this is also known as f of g of x. This means that the x variable of f of x is now substituted by the entire expression g of x. In this case, for this example, our function now is, instead of x to the power of 7, this x is now changed into the entire g of x. Hence, we will have this form here, x cubed minus 4x squared plus 5x minus 10 raised to 7. This is an example of a composite function using the two given functions. Then, if you are going to solve for the derivative of this composite function, okay, you might need to apply here expansion for this exponent, but take note, you will have a lot of terms and you may be using more than one rules, and more importantly, the rule of differentiating sum or difference. But the chain rule talks about a specific type of rule intended for this without even expanding this. And this is the chain rule. You take the derivative of the function, taking into consideration this as just one term and applying here the power law, or the rule for differentiating the power, okay, and then multiply this by the derivative of this entire expression. So this is the chain rule, or the rule in differentiating a composite function. Again, you take the derivative of this entire expression, splitting this into one using only this exponent, applying the rule of power, then multiply the result by the derivative of this given expression here. Now, aside from this example, you can also have a lot of examples where chain rule is very important. Say, for example, another f of x here, let's say x to the power of negative 4, and then your g of x is, let us say, a quotient of x plus 1 over x. If you will have this composite function, you will have this entire function raised to the power of negative 4, because you will have this substituted by the entire g of x. And this is still solvable using the chain rule. Another is, if we're going to talk about trigonometric functions, let us say sine x, and then your g of x here is x cubed. Your f of g of x will be sine of x cubed. Now, we know the rule in differentiating sine x, but since the angle here is x cubed, you're going to apply the chain rule as well, as taking this into one, okay, taking this as one angle, and then multiply. So for trigonometric function, it will look like this. Derivative is, you're going to treat the entire trigonometric function still, okay, this one here. Then you're going to take the derivative of this angle here, which in this case, again, g of x. Same formula. Another situation is if you have this situation here. Let us say you have your x to the power of 9, and then your g of x is cosine x. So your f of g of x will be equivalent to the 9th power of your cosine x. Again, treating them as one using power law, or the rule for power, and then you multiply it by the derivative of this. So basically, all of this can be solved using the chain rule or the rule in differentiating composite functions. We may have some of these examples on our next few videos. At the same time, the proof for this rule will also be made separate. Just an illustration why this is called chain rule, because look into this one here, the formula itself. Take note that f of g prime of x is equal to f of this one here, the derivative of the entire expression, treating this as 1 times g of x. Take note of what happened here. This is why it's called chain rule. Because of this, let me change my pen color to red. You are going to, this one here, this equality, you're going to take the derivative of this, then the derivative of that. Okay, so writing here, it looks like this, derivative of this, that, and if there are more, it looks like chain. Okay, that's why it's called chain rule. An example for that is this. Say for example, you have nested composite functions. Let's say you will have here f of x is equal to sine, and you have here x plus 3, and this is raised to 5, right? So the one thing you need to do here is there are two different expressions here. You have an exponent where this is under that, and your angle here is still another one. So what you're going to do here is this. Treat the entire expression. So you are going to take the derivative of the entire expression. So that is actually what will happen here. That one, then times. Of course, you're going to multiply this by the derivative of this, right? So that's why you will have another one here. And since your angle is still another one, so you will still have another rule here. That's why it looks like a chain if these are actually curved to that. It's just like the chain, okay? So you will have something like that, and then you will have something like that. Those are chains. That's why it's called chain rule. Nested composite function. So generally, that's why it's called chain rule. Thank you very much for watching. So what are you waiting for? Subscribe now.